Hello, Tanya Laird here, and welcome to part 1 of lecture 12 of ENGR 231 Engineering Statics. In this portion of the lecture, I want to go over some of the details and some of the topics of internal forces in members. So let us consider member internal forces. Member internal forces. So in previous cases, we have looked, or in previous lectures, we have looked at the kinds of internal forces that can exist inside members. Well, in particular, though, we have looked at one internal force, and that is axial force. So what we've looked at previously, we have seen the types of forces that will exist within truss members, and those are axial forces, namely tension and compression. So we defined that if we had a truss member, or a member that was straight, had no loads applied at anywhere except the joints, and had pin joints, then in this case, this type of member would have only a single axial force running all the way through it. Some sort of P here and P here. And if this is going to be in tension, then the force arrows will point outward from the member. And if it's going to be in compression, they'll point inward. Just a simple P and P. But this is actually, as we discussed previously, the truss members are a very special case of member. It's very uncommon that you will have all of those conditions met, where all of the both ends of the member are pins, that the member is entirely straight, and there are no other forces applied anywhere except at the joints. Now, we've also looked at frames. In our previous lecture, lecture 11, we looked at frames. However, we only looked at the external forces rather than the internal forces present at frames. So we only considered external forces on members. Only considered external forces, not internal forces. So today I want to move on to talk about the general cases of what kinds of forces can exist within members. So member internal forces, general case. So again, the trusses are a specific case, a particular type of member, but we're going to be looking now at the general case for all of the main forces that can exist inside members. And of course, we could find exceptions to this and other examples, but well, first let's talk about this. So general forces in members. So a first one that I will briefly mention is torsion. Now, this is a bit beyond the scope of this class. I don't really talk about it much in statics. It doesn't connect very well with the frame diagrams and the type of things we do in this course. But if I am listing all of the main types of forces that can exist within members, I should mention torsion. So torsion is, I'm just going to include this at the start, but it's not going to be one of our main ones that we're going to look at today. Torsion is a twisting along a member's axis. So if you have a member, and let's consider a simple beam. So most of the forces we're going to look at today are going to be applied downward or along the sides or up and down, whatever it may be. But imagine if you could look at this from the cross section. What if this thing imagine this thing has a cross section here. So we're looking at this edge on. Torsion is a twisting about the cross section here. So it's going to cause this thing to, basically it would cause, if I applied a torsional force in the middle of the beam, basically the beam would end up twisting along the axis. That's torsion. Now, again, that's not necessarily something I want to look at today. That's a bit beyond the scope of this class. To get anything useful, to analyze these in any useful manner, you really need to get to mechanics and materials, which is the course that follows after statics usually, in most curricula. So the ones that I really want to look at are the primary forces we receive by cutting frame diagrams. And these are, well, first you have axial force. Second, you have shear. And finally, you have moment. an internal bending moment. So let's consider this. Let's discuss both axial force, shear, and moment. Imagine if we have a member, and let's say it's continuing on this location, or maybe I could show it like this. Maybe I'll draw a simple beam. So I have a beam, and I'm going to cut it. Well, let's say it's originally like this. I have some beam, roller support there, and I'm going to apply a general loading to the top of this. Just some arbitrary loading. The whole point of this is that I don't know, that I'm describing this in terms of a general case. I don't know exactly what loading is present in this particular beam. So let me show you what kind of loads that can exist in here. Oh, and let's just say there's some, let's include both horizontal and vertical loadings. Let's say there's some sort of arbitrary loading applied on the other side, on the side too. Something like that. Okay. What I'm going to do is I'm going to cut this beam, and much as we've done previously when we've looked at the method of sections and trusses, I'm going to say when I cut this here, what kind of internal forces can exist within the member. So I'm going to cut this, and I would have the same general loading up to the cut and from the side there. And I'll just show this as a cut surface. And then let's look at the loads. So I still have the same, whatever general loading was there before to the left of the cut is still going to be there. And same here. Now, there's going to be some forces on this. The first force I might call N. N is your axial force. It acts along the axis of the member. This is the exact same type of force that the exact same type of force is the single force trusses carry, and it's going to be either tension or compression. And we remember from our discussion of trusses that tension is positive and compression is negative. And compression is negative. Then I can have shear. And on the next slide, I will discuss the positive and negatives of shear in a moment, but I just want to define these right now. So I have a shear here, and we use the variable V, a capital V, to describe shear. V is shear. So axial force, tension, or compression is easy enough to understand, but what is shear? Well, shear is a shearing force, is the best way I can describe it. If you look at a element and consider the type of forces that would shear it apart, imagine two forces. Imagine a small differential element of this. If I cut away just one little differential element here, a dx or something, there is going to be one shear arrow here and another shear arrow here. So it would be very much like a, well, think of a pair of shears, like a pair of scissors. You have a shearing plane here and a shearing plane here, and this thing is being sheared apart. It's shear fundamentally is a force that is perpendicular to the axis of the member, but not one that is causing bending, at least directly. So we have that. And then finally, we have moment, internal moment. M. Moment or bending moment. Moment, or sometimes called bending moment. And what separates bending moment from torsion is that moment is bending along an axis perpendicular to the axis of the member. So here you have your member axis in this direction, and if you imagine drawing an axis into the page here, this moment here would be twisting about that axis. Moment is rotating like this. It's rotating about an axis that is coming either into or out of the page. So that's moment or bending moment. Two different names for the same thing. And so if you have an element that's undergoing bending, it wants to distort like this, for example. Well, something like that. And that would be you couldn't do that with just simple moments on either end in that particular shape, but that's okay. So you have a moment and a moment. So our three main forces are going to be axial force, shear, and moment. Axial force is going to want to pull or compress the member. shear is going to want to break it along an axis that is perpendicular to the member axis, or on a plane that is perpendicular to the member axis, and moment is going to want to cause the entire thing to bend, or for a simple beam like this, it would want to cause it to sag downward. Next, I would like to discuss how the sign convention for shear and moment, or maybe I can just mention all of these really quickly. Internal forces sign convention. Sign convention of internal forces. So first of all, let's consider axial force. Well, this one's easy. We've already discussed this. It's just compression or tension positive and compression negative. And compression negative. Now, where it gets tricky is when you're looking at shear and moment. And the tricky thing about this is, just like with moments, where if you remember to our previous discussions of moments, you could not just say, oh, a force is upward, therefore it causes a positive moment. Well, shear is kind of like that in the sense that there's no simple rule of, oh, an arrow is going upward, therefore it's positive, or oh, the arrow is going downward, therefore it's negative. Shear, the state of being in positive or negative shear is a state that a chunk of material has, that a section of a beam or a column experiences. So shear, I'm going to label this as positive shear. So consider two different differential elements. I'm going to show one with positive shear forces on it and another with negative shear forces on it. So let's say you have a, for positive shear, for example, you're going to have something like this, a downward shear arrow on the right and an upward shear arrow on the left. And in negative shear, you're going to have the opposite. You're going to have a downward shear arrow on the left and an upward shear arrow on the right. This is the state that produces positive shear. Simply having an upward arrow does not mean you have positive shear. Simply having a downward arrow does not mean you have positive shear. This is a common error that students make when learning statics and mechanics of materials. Oftentimes they'll see an upward arrow and go, oh, I know up is positive, up is good, so I know that up must be positive. Nope, wrong. Because here, you notice on negative shear we have an upward arrow, and on positive shear we have an upward arrow. And on positive shear we have a downward arrow, and on negative shear we have a downward arrow. No, what makes positive shear is not simply a direction of an arrow. What makes positive shear is the relation on the element itself. So you have an upward arrow on the left, if you have an upward force on the left side of an element, and a downward arrow on the right side of the element, this is what creates positive shear. Now you can't have an upward shear arrow on both sides because that wouldn't be in static equilibrium anymore. We're talking about a small differential element where the shear can be considered the same on both sides. And so again, if you have an upward arrow on the left side and a downward arrow on the right side, that element as a whole, not one side of it, is in positive shear. For a differential element, again, it's small enough that the difference between left and right is minimal, and so you can't really have upward on both sides or something like that. Then negative shear, again, is defined as a downward shear arrow on the left and an upward shear arrow on the right. So in other words, if you have a member, let's say it's simply supported and it's supported by a single arrow over here. All right, so let's say you have an element here and you have a force on the left, an upward force. Let's say this is a section of a beam that you've cut out. You have a cutout section of a beam, and you want to see if this is in positive shear or negative shear. Well, later we'll get on to actually analyzing and calculating these, but if you wanted to assume that you had positive shear, you would have a downward arrow like this at the right-hand side of the cut. Then in turn, on the other side of that cut, you would have an upward arrow, equal and opposite forces. So you'd have a downward arrow on the left-hand side of the cut and an upward arrow on the right-hand side of a cut. If you had for example, a simply supported member with downward loads that you cut you know, just something somewhere right here in the middle. You'd have an upward force arrow on the right from the support, and then overall, if you were going to have positive shear at this location, you would have to have a downward shear arrow on the right and an upward shear arrow on the left hand side of the cut. And so, and again, that would be what would be needed to make this thing a static equilibrium. So really, this now, as far as why this is positive shear and why this is negative shear, really this comes down to how we like to define the bending. We like to have positive bending be in sort of a smiley face direction, and we also like to have our loads be pointed downward. And this this type of definition of shear, honestly, it is kind of just it's kind of just our preference. We could define positive shear as the opposite direction; that would work just as well. But we design our systems around as engineers, we simply chosen to have this be our sign convention, and we use this for all of our shear calculations. And then finally, moment. Moment is a lot simpler. It's just based off of whether the thing bends upward or downward. So if you have a beam, or a section of a beam, or a section of a column, or whatever it might be, that is bending like this is negative bending. So if I apply forces like this, I suppose I should use red to be consistent with what I've done elsewhere. Maybe I'll actually just draw them like this. Or actually, you know, if I've been used to doing positive first for everything, I suppose I should do the same here. So I'll have something like this. And this is positive bending. And this here is negative bending. And we can talk about what kind of member end forces would produce this, but hopefully that's fairly straightforward, or hopefully this is fairly intuitive. So to get this type of bending, you'd have to apply a moment like this, an M and an M. And to get a moment like this, you would have to apply an M and an M, something like this. And one simple way of remembering this is positive bending. Well, think positive thoughts. Positive bending is sort of causes this thing to bend in a sort of smiley face pattern, and this tends to cause things to bend in a frowny pattern. So we want to think of a really easy and stupid way of remembering what direction positive bending is. Think of just a simple smiley face. Now, truth be told, why do we define positive bending like this? Well, in most engineering applications, if you have most beams, for example, you're far more likely to encounter systems with more downward loads than upward loads. So if you think of a building or something like that, most of the vertical loads in a building are going to be downward. There are some upward loads, but most of the downward loads will be things like the actual weight of the beams, weight of the floors they're supporting, weight of any people and equipment, that kind of thing. So you're going to encounter much more downward loads than you are going to encounter upward loads. So you can actually have upward loads in a building. For example, roof uplift is a common one from wind, but you're more likely to encounter downward loads. And so in most engineering applications, you encounter this type of bending shape way more than you encounter upward bending like this. So I really think this is the reason we define positive bending like this, and that's simply because in most engineering applications, you're far more likely to encounter downward loads than you are upward loads, just with any type of building or machine or something that is going to exist on the Earth's surface, because you have downward loads, etc. Gravity, weight, that sort of thing. Finally, I'd like to talk about, as a final note on sign convention for non-horizontal members. This is a common question that also gets asked, is also commonly asked. So how do you figure out your sign convention, especially for something like bending, when you're dealing with non-horizontal members? So for example, it's all well and good to say for a horizontal member, okay, well, positive shear or positive moment is going to look like this. But what about if you're dealing with a column? What if you have a column, or a beam column, I suppose in this case, something like this, and it's bending like this? Do you call bending like this positive, or do you call bending like this positive? What if you have a column? What if you have something like a frame where you have a column, a beam, and a column, something like that. And maybe this one's bending like this, and this one's bending like this. These have to be pin joints or something like that. We'd have to have some really interesting loads to get this. Well, how do you know whether these are positive or negative? Well, at that point, our basic, simple definition of positive and negative bending does break down a bit. One common thing you can do if you have a really complex frame is just say that all bending downward or to the right is positive. That's one simple way. But really, it ultimately comes down to how you define the positive and negative axis for your beams. So especially when you get to higher levels of structural analysis, often you'll decide when you're analyzing a beam or a column or a member in general, that this end, I'll just declare, this is my zero end, and my x coordinates are 0 and then in a certain direction positive. And in fact, we'll actually see that soon when we get to looking at shear and moment functions in beams. We'll actually have to define 0 at a certain point and then calculate a function in terms of that 0 that a certain direction is positive. So really, for horizontal members, it's relatively simple. For vertical and angled members, I just try to stick to downward being positive as much as possible. Downward and to the right and to the right. But again, the to the right especially is incredibly arbitrary. I should probably say is positive as much as possible. So for example, if you have one case where it's relatively easy to stick to that is an angled member. So if you have a member like this, something like this, and you applied a load to it, well, because it's a substantial portion of it is horizontal, it'd be very easy just to stick to the, well, down this direction here is positive bending, relatively easy to stay with. But again, it can be quite tricky, especially when we get to more advanced cases, or especially when we have very complicated frames and things like that, and it can be very difficult to define which is the positive and which is the negative. And in that case, it really, ultimately, in those cases, it really does come down to personal preference and whether you want something to be in positive or negative bending. Once you get out of the horizontal or the purely horizontal or the mostly horizontal cases, the classical meaning of positive or negative bending really does lose a lot of its meaning. Okay, all right, so this describes the basic idea of what kind of internal forces can exist in a member. In the next portion of the lecture, we're going to look at how you actually start finding member internal forces by applying the method of sections to a single member rather than to, say, a section of a truss. All right, that'll do it for now. Thank you for watching. Let me know if you have any questions. I'll see you all soon for part 2. And as always, thanks.